recently decided to add some security feature to their PLC. And today we have Tobias and Ali, and they will be sort of telling us what they managed to find this PLC. They both come from Ruhr University Bochum. Tobias is a recent acquisition as a doctoral student, and Ali is a postdoc. So let's give them a hand.
Where is our slide?
On the presentation mode.
We are. Let's say it again. Yes. Okay. Welcome to our talk, a deep dive into unconstrained code execution in Siemens S7 PLCs. My name is Ali Abbasi, and as mentioned before, I'm a postdoc at Chair of System Security at Ruhr University Bochum, and here is my colleague.
I'm Tobias, or Toby. I'm very glad to be here. It's my 5th time at the Congress, and now finally able to give back in a way, so I'm very excited about that. So let's get into it. So first, about the plan of the talk. We want to give you a little bit of a background of what PLCs, which is programmable logic controllers, are all about. Why we might want to use them, in what kind of setting, and then we want to go into the specifics of PLCs in the Siemens case. First, we look a bit at the hardware, and then at the software afterwards, and the different findings that we had. At the end, we will show a demonstration of what we were able to achieve, and conclude with some remarks. So first of all, process automation. So we all know it, or maybe we do it ourselves, or we know somebody who does it. We put in some devices in our smart home, if we call it smart already. And we try to automate different targets, or different things, to make our lives easier. Things like turning up and down the heat. We might not want to do that our own. We might not want to overheat or underheat. And what we do is basically have some sensory systems inside our homes, as well as some devices that interact with those sensors. In this case, we might have a thermostat and a heater, and we want to adjust our temperature based on the thermostat. There are pretty simplistic solutions like this for smart home, but what do we do if we have very complex control loops, for example? Here we can see on the left bottom corner a pretty complex looking picture. Some operators sitting in front of what we call an HMI, a human machine interface, which is basically an aggregation of all the information of things that go on in a factory, for example. We need different sensors in this factory, and we need to steer different motors and stuff like this. So we need things in the middle to kind of control all of this. And we do this using PLCs. Here we can see a setup, how it could look like. So basically you have a set of inputs, as we talked about, and a set of outputs. And we have some logic going on in the middle. And what we typically deploy is a PLC, a programmable logic controller, and some logic in the middle. There are different technologies that can be used, for example, structured text or ladder logic, which gets downloaded onto the PLC, and then which steers outputs based on the inputs that it gets. Here we can see some applications of this kind of thing. For example, a chemical plant, an electric grid, or some manufacturing. All of those components are pretty critical to the workings. Either we see it in our everyday lives, and sometimes we don't really see it, but they are in the steering everything in the background. And we really don't want those systems to get compromised. For example, if you went on to Google and looked something about disasters in chemical plants, you could see some melted down plants just because of some malfunction in a system or so. And we really don't want this to happen, neither on an accidental, but also not on a malicious basis. And this is why we want to secure all the processes going on in factories and the like. We've seen some of the recent attacks. So it started kind of in 1999 with a first initial reconnaissance base mainly. And then we had some more advanced attacks in 2010, for example, where we saw Stuxnet, which was very much a really intricate operation. If you think about it on a technical level, what all went into it, what different skill sets were involved, it's pretty impressive. And then in the more recent time, we had some issues in the Ukrainian power grid, which in 2015 and 16, just before Christmas, some lights went out for quite a while in some cities there. So quite a bit of impact. So to give you a bit of background on Siemens PLCs here, when it comes to market shares, we can see that together with Rockwell Automation, Siemens actually has more than 50% market share in the market. And obviously, if we tackle some devices that introduce some security, it would be interesting to look at those with the biggest market share. This is what we did here in the Siemens case. Here we can see the actual PLC that we will focus on in this talk, which is the Siemens S7 1200 PLC. It's one of the smaller PLCs, not quite the smallest. There is the logo as well, which is more of a playing around example. But this is the one that it's still pretty accessible to researchers in terms of costs. So it's like 250 for the PLC. Then if you need a power supply, it can add the same. So as long as you don't break too many, spoiler, we broke quite some, or you don't drop them, or something like this, then you're pretty fine. So you can kind of get the resources to play with those devices. We have different applications, and we talked about them before. So here's what an unboxing of a Siemens S7 1200 PLC would look like. We have the top view here. In the left picture, it's only one of different PCBs which are layered onto each other in this case. But the real magic goes on in the top PCB, which is the green one that we see here. Looking at it a bit more in more detail, we have the top view on the left side, which shows the different components that really make the PLC tick. For example, the ARM CPU that we have, or different input-outputs that we can connect to PLC, as we talked about before, which they need in order to steer different parts of the system. And then we have the flash chip on the top side as well, which is a bigger flash chip holding the firmware of the actual PLCs, which we will talk about a bit more in detail later. On the flip side, we have on the right picture the bottom side of the first layer PCB. And as we can see here, this is where the bootloader chip resides, which is an SPI flash chip of 4 megabytes holding the code of the Siemens PLC bootloader. Here we wanted to have a detailed view on what the actual processing unit inside this board actually looks like, and what you can do if you really want to find out. You can do some decapping, and this is what we see here. The result of this, we can see that at the core of it it's a Renesas ARM Cortex R4 from 2010. And if you afterwards are more juggling with the software side of things, you may also want to find out the actual revision number, what it supports inside the ARM standard. And what you can do there is use a special instruction which resides in the ARM instruction set, and you can decode the different bits on it, which we did here, which you can see here for reference. So if you really want to know what's going on, you can take apart those bits and make sure you're actually working with the hardware that you expect to be working with. So here's where we come to the memory part of the hardware, and this is where I leave you over to Ali.
Thanks. Now that Tobias unboxed the PLC for us, now I'm going to talk about quirks and features in the PLC. So as mentioned before, it's a Cortex R4, revision 3. It's a big endian instruction set, and it's also only have MPU, so there is no virtual memory, basically. There are multiple RAM sizes depending on which year you bought it or which variant of the S7 1200 you buy. And also multiple SPI flash and multiple different types of NAND flashes. The most significant one difference is like in the RAM, which sometimes they use Wingbone and sometimes they use Micron Technologies. Recently, at least, Micron Technologies RAM. It's a LPDDR1 RAM. With respect to SPI flash for bootloader, so it's again, depending on the variance, between 1 to 4 megabytes SPI flash. It contains different banks of each size, 5 and 12 kilobytes. And basically what the bootloader does is that beside the typical actions of the bootloader, which is like configuring the hardware, is like verifying the integrity of the firmware before it being loaded. So we actually did some X-ray tomography of the PLC. So it's basically 3D, so the PCB is basically rotating here because we wanted to also do some hardware reverse engineering part. And somebody in university had something, so we didn't have to go to our dentist for X-ray. So here is like a quick 15 minutes X-ray, which is not that good. But once you go in deep, eventually what you will have is like this. And you can actually just, it's like a software animation. You can go inside PCB and see all the layers. It's like amazing. So it has 4 PCB layers. And so beside VCC and GND, there are 2 layers of PCB connection, basically. So let's look at the startup process. Again, startup, as usual, some hardware configuration happens. So vector interrupt controller, for example, like lots of these handlers for different modes in ARM. And then CRC checksum of the bootloader itself, which is easily bypassable because you can just overwrite that CRC when the bootloader, especially in the 2017-2018 variant of the Siemens PLC, allows you to overwrite the SPI flash. And also eventually check the CRC checksum of the firmware before basically loading it. The size of the bootloader itself is like 128 kilobyte. It's really even less than that because half of it is just like 0xFF. Siemens multiple times changed. There are different versions. I think in 2 years we saw like 3 variants or 4 variants of the bootloader. So it was evolving. It was not something that's everybody forgotten about it. So generally, as mentioned, so you have the first stage of hardware initialization, and then basically bringing the bootloader to the RAM, and basically checking the bootloader CRC checksum, so make sure that it's not manipulated, which again easily can be bypassed. And then a second stage of the hardware initialization happens, and then at this moment it waits for a specific command for half a second, and if it receives this command, it goes to another mode, which we'll discuss later. Otherwise, it basically prepares some CRC checksum table for the firmware, and then it tries to load the firmware, and then eventually it just remove the memory barrier, the SY instruction, those who knows about ARM, and basically map the firmware to the memory. So the name of the operating system, it was not mentioned before, is Adonis. We know it from different ways, actually. So first, in the references in the firmware, we see lots of references to Adonis, but that was not enough for us. So we actually looked around to see if like there is any reference to it, and well, LinkedIn is one good open source like reference. And here is like one employee actually talk about a Siemens developer who talk about like working in Adonis. I don't know why he put Windows and Linux beside Adonis, but like he says that like he worked on this. And so it was not enough for us, so maybe it's some OS we don't know. And we look again further and further, and we find this thing, which was the best indicator. So a Siemens developer engineer mentioned that he worked on a kernel software development for Adonis real-time operating system, which is a good sign for us. It means that we are right. So now that we know about the naming, and we're sure about that, let's look at the components. So it's actually a start in basically 440, and basically then initializing the kernel, and then lots of routines for initializing different components of the operating system. I don't think Siemens actually generalized it in this way. We don't have such thing in their firmware, but we actually did it like that. So we generalized it to 2 groups. Some of them are core services, like Adonis real-time operating system services, and some of them are related to the automation part. So those people who are like in the automation part, like writing ladder logic and stuff like that, those commands on function codes which are available in Siemens, they actually know these are like more automated related services. So you have Profinet, AWP, or automated web programming, MC7 JIT parser basically for their ladder logic or different kind of SD, like basically their own JIT compiler inside the PLC. And you also have the OMS, this configuration system, which is very related again to the automation part, core part of the automation system. And of course, alarm, central I/O, and stuff like that related to automation. In the operating system part, so lots of these usual things. So file system, so PDCFS, which Tobias talks later about it, the TCP/IP stack, some C++ libraries, which is not from Siemens, it's from DynConveyor, and MiniWeb web server, MWSL parser, or MiniWeb scripting language parser, and lots of different subcomponents, which is usual in operating system, like any operating system you can find them. Also, there are some references to CoreSite. I don't know how many of you know CoreSite or how much you work on ARM, but basically CoreSite is something similar to Intel Process Tracing or Intel PT for tracing applications, and can be used for getting code coverage, for example. And the hardware part is very well documented by Thomas Weber. In this year, it's not yet ended this year, so this year, Black Hat Asia. But I have to warn you, because I received some emails, some people ask about that. If you